Okay, welcome back. This is part 2, and there's a question from Brian about the ordering of the KGB elements, and that's a good question. So there is an ordering, there's a partial ordering on KGB, which is given by the closure relations of the corresponding orbits, of course. And so, well, when I come to the software, I'll do an example, but let me just show you this picture here. So here, for example, is the Hasse diagram for KGB for SP4, and the lines indicate closure relations. So there are 4 closed orbits, 0, 1, 2, and 3. And there's one open orbit up here, which is 10. And sorry, I'm in the wrong window. There we go. 0, 1, 2, and 3 are the closed orbits, and up here is the open orbit. And then here are the closure relations. And so you see that, for example, 4, 5, and 6 are one step up from the bottom, and then 7, 8, 9, and then the one at the top, which is 10. So the order isn't terribly, the total order isn't well defined, but there's a partial order which the output respects. Okay, I'll come back to that example. Let's see. So let me go back to the slides for 1 or 2 more things. So here's where we were, and I've got 1 or 2 more things to look at. So let's talk about discrete series now. So let's fix this XB, and excuse me, define F to be the inverse image of the identity in the Weyl group. So these are the elements X. Let me go back to the previous page. The elements X which map to the identity. Well, this map is this Weyl group element being the identity is just to say that this corresponding element X is actually in the Cartan. And so this P inverse of the identity is the elements of X which are actually in H. And this is called the distinguished fiber. And this plays an important role. And in particular, this F, what does it do? Well, it parametrizes the Borel subgroups containing the compact Cartan, the K conjugacy classes of them. And if you think about it, that parameterizes the discrete series representations with a fixed infinitesimal character. For example, if you fix rho, the discrete series are parameterized by these Borels up to conjugation by K. And explicitly, if you have an element X, you can write it as W applied to the base element, and that's giving you the discrete series representation with Harish-Chandra parameter W rho, or whichever fixed infinitesimal character you're talking about. Oops, excuse me. Sorry, there we go. Okay, so that's the sort of new ingredient when you're talking about representations associated to the Cartan, which is not split. The element X is not only telling you which Cartan, but it's telling you a Borel for that Cartan, and it's a K conjugacy class of Borels for that Cartan. Okay. All right, so let me pause there and go back to the software. Give me a second. Okay, so now I'm going to go look at some examples using the software. Where are we? I believe this is the software. Okay. All right. So let's take a look. So let's start simply. Let's say G is SL2R. Oh, that was a mistake. I should have said G colon equals SL2R. There we go. And let's, there's a command print KGB of G. So, whoops, excuse me. So this says that KGB has 3 elements labeled 0, 1, and 2. And over here at the end, well, after the number sign is the number of a carton. So these two KGB elements have to, are the corresponding carton is the compact carton, and this KGB element goes to the split carton. And let's set X is equal to the 0th element of KGB. And well, let's look at the discrete series. So let's set B as the block of the trivial representation of G. And now Mark was encouraging me to do the following. I've been doing this a lot. For P and B, do print S P. And Mark recommended doing the following. Let's define a command, show, and show is the following. If the argument is a list of parameters, and I'll call that params, and I'm going to say, sorry, for P in params, do print S P odd. Okay, so I've defined a command called show, which takes an argument, a list of parameters, and it runs over the parameters and prints them. And in addition, it has this void thing here, which says it's returning the void value. And so if you use this version, well, for one thing, there's less typing involved. And also this statement here for P and B, blah, 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 it has the slightly annoying feature that it returns this empty array, or this array of whatever these things, this array. And well, I don't want it. So by putting in this void here, when I do show, I won't have to look at that. So I'll be using show from now on when I have lists of parameters to look at. And so these two parameters are the discrete series, X is equal to 0. This first one here, X is equal to 0, and this one, X is equal to 1. So let's look at B bracket 0, and let's look at B bracket 1. Okay, so this is one of the things that I get asked most often about the software. What does this mean? Well, this is saying this is a discrete series representation, and the Harishanda parameter, the character of the Harishanda parameter is lambda, which is 1 in the usual coordinates. This discrete series, it has the same lambda, which is to say 1. The thing which is different is X. And what that means is that this you have to fix an X to talk about a K, to talk about a real group. So let's fix X is equal to 0. Then lambda is rho in the usual coordinates. On the other hand, if you come along with X is equal to 1, in order to identify this representation, which is a representation for this X, with a representation of the group where X is equal to 0, you need to conjugate 1 to 0. And, excuse me, X is equal to 1 to X is equal to 0 by using S alpha. And in doing so, you will conjugate lambda to minus lambda. Okay, so there's a way to the software helps to make that a little more comprehensible. And so I'm going to work I've decided that I actually want to call it XB to indicate it's this fixed KGB element. So XB is KGB element 0. And I can ask for the Harish-Chandra parameter of the, well, let me remind you, B bracket 0 is this parameter. And I can ask for the Harish-Chandra parameter of this with respect to this XB. And what I'll get is rho. On the other hand, if I look at B bracket 1, and I ask for the Harish-Chandra parameter of this representation, with respect to the original XB, I get -1. That's the punchline. So one of these is the holomorphic discrete series, and the other one is the anti-holomorphic discrete series, given by lambda is equal to 1 or -1. And, well, which one you call holomorphic and which one you call anti-holomorphic isn't well defined. I could have chosen, instead of choosing XB to be 0, I could have chosen XB to be X1, and that would have given me the opposite convention. So in any event, so that's the basic idea. Now, one thing that's helpful is you can, let's see, what do I want to say? Well, let's do a slightly bigger example. Let's say G is equal to SP, sorry, G, my caps lock key, G is equal to SP, excuse me, for R. Okay. Now there's a command in all parameters, I believe it is. Let's set D, well, let's check the command. What type? Discrete series. Discrete series has a couple different versions. The second one is the one I'm interested in. You give it a real form and a rational vector. Oh no, I'm sorry. The command that I want is all discrete series gamma. There we go. So typically these commands, like principal series, is giving you a single principal series. And so this command here that I was talking about was giving you a single parameter. But these commands, which have all at the beginning, are giving you a list of parameters. And so the syntax is, I'm asking for all discrete series of a given real form with a given infinitesimal character. That's the gamma. So let's set ds is all discrete series by gamma of G with rho of G. Okay, so there are 4 discrete series of SP4. And they all have the same lambda. Of course, nu is equal to 0. They have the same lambda, which is equal to rho. And there they are. And the thing that's different about them is the x. Okay. So, well, how do I identify these with the discrete series of SP4 that I understand? Well, the way you do that is the following. So I need to choose this XB. And how do you choose XB? Well, it should be one of these guys in the distinguished fiber, which is X is equal to 0, 1, 2, or 3. So let's start by setting it to be 0. Excuse me, 0. Whoops, I forgot the colon. Okay. And let's check what is K of this fellow. So this is a new command, K naught. The naught refers to the fact that I'm just interested in the identity component of K. Well, in this case, it's connected in any event. K naught of XB is a compact connected real Lie group with Lie algebra SU2.U1, which is to say it's the group U2, which is the maximal compact of SP4. Let's set K equal to this. Okay. And let's look at the simple roots of K. Well, that's disappointing. It's the root 1, 1. Humans want the compact root to be 1 minus 1. And, well, that's not the case here. So what I recommend is that you try a different x. So let's set x is equal to kgb1, and let's look at the simple roots of k naught of this xb. Still 1, 1. Let's try 2 simple roots of this. There we go. So somehow kgb element 2 is the one which is going to give me the coordinates which I'm most familiar with. So let's use xb is equal to kgb element 2. And now say for p in the discrete series, 2 SP, and let's look at the Harish-Chandra parameter of p with respect to this fixed xb. And that makes me happy. So if you look here at the end, you see that the Harish-Chandra parameters that I'm getting are 2 minus 1, 1 minus 2, 2, 1, and minus 1 minus 2. And for those of you who are familiar with the discrete series of SP4, those are the usual Harish-Chandra parameters of the 4 discrete series. This guy right here, with Harish-Chandra parameter 2, 1, that's the holomorphic discrete series. This guy here is the anti-holomorphic discrete series. And these two are the large discrete series, this one and this one. So to check that, there's a little bit of additional information I could do. Let's look at the I got the syntax right there. Yeah, there we go. So I'm looking at the status of the simple roots for the corresponding x's. Okay, so the software always chooses x0 to be, for the quasi-split group, to be the large Borel, which is to say both of the simple roots are non-compact. And, well, the simple roots in this chamber are the root E1 plus E2 and minus 2E2. And since we've chosen the usual, since I've chosen xb is equal to 2 and 1 minus 1 is the compact root, that's the usual thing. And similarly here in this chamber, both of the simple roots are non-compact. But in this chamber, the first simple root, E1 minus E2, is compact. And in this chamber, similarly, the first simple root is compact. So that's one way to pass back and forth between parameters as given by Atlas and the Harish-Chandra parameters of the discrete series. Okay? All right, let me pause there, see if there are any questions. Someone says, I also had a problem loading all parameters.at. Oh, thank you, Adam. Yes, that's absolutely correct. There's there's a stupid extra G in the very first line of the file. And I'd noticed that at some point. I thought I'd uploaded a version without it, but apparently I didn't. So I'll fix that. But in the meantime, delete the G from the very first line. Thank you. Okay. All right. Okay. So now there's a command to go the other way, which is to say the following. There's a command discrete series, which says if you give me a KGB element and a rational vector, I'll hand you a parameter. And so the KGB element here is the XB, the base point. So for example, let's set P is equal to the discrete series representation XB with Harish-Chandra parameter 2, 1. Well, there you go. That's this parameter with x is equal to 2. And the lambda is equal to 2, 1. So, for example, if I wanted the large discrete series, I'd take 2 minus 1, and that's going to give me the discrete series with x is equal to 0. So what the software is doing is it's this Harshanda parameter that you're giving 2, 1 or 2 minus 1, it's conjugating that to what is it there? It's conjugating that to 2, 1, and then it's applying W, or maybe it's inverse W, I'm not sure, to XB. So for example, since this is 2, 1 itself, I'm getting back XB. But here, in order to conjugate 2, 1, 2 minus 1 back to 2, 1, you have to apply the reflection in the long simple root, and that takes x2, excuse me, yes, x2 to x0. So it's actually possible to see that directly in terms of the Weil group. So let's see how that works. I think there's a command move. No. Well, let me do it this way. Let's set W is equal to generate W of G. So this is the entire Weil group of type C2. And the software knows how this acts on, well, first let me look at it. For W and W do. Okay, so what this W is, it's a list of pairs. The first entry is the root datum, and then the second entry is the product of simple roots. So ignoring the root datum for the moment, which is always C2, the elements are the identity, 0, 1, 1, 0, and so on. And here's the long element of the Weil group at the end. Okay, and let's do the following. For W in W, do printfs act, or no, sorry, the cross action of W on XB. Okay, so what this says is that this action of W on X, the identity takes, XB is KGB element 2, takes it to itself, and the reflection in the first simple root takes it to itself. And that's because this simple root 0 is the compact root for XB. And similarly, the reflection in root number 1 takes KGB element 2 to KGB element 0, and so on. Okay, so notice that the action of the Weil group on this KGB set, there are 4 KGB elements, 0, 1, 2, and 3, and it's acting transitively on them, and the stabilizer is WK. Okay, so for example, you can do the same thing where instead of looking at the action on this compact carton, you can look at the action of the Weil group on KGB for the split, the KGB element number 10, and it acts trivially there. That is to say, on the split carton, there's only one KGB element, and the stabilizer is the real Weil group, which is the entire Weil group is a real Weil group, and so the action is trivial there. Okay, so that demonstrates the action of the Weil group on KGB. So let's look at another example. Let's see. Well, one thing is, let's go back and so back here, well, let's do this command again. So this is showing me the 4 discrete series, and this is in the coordinates that I'm familiar with. If I hadn't given this argument to the Harshanda parameter, I would get something rather confusing. What this is doing is, well, let me just put in explicitly KGBG0. Right. So if you had decided that you wanted to define your group where K was given by X0, then the four Harish-Chandra parameters would be these. So the non-compact root in this case is 1, 1. And so, for example, if you apply that to 2, 1, you get -1, -2. And so you see that these four elements here are indeed representatives you start with 2, 1, and you apply the Weil group to it, and modulo the action of WK. This is the four representatives, but they're just a little bit weird looking because the compact root is 1, 1 instead of 1, -1. Okay. Let's do a slightly bigger example. Let's take G as SP6R. And let's set F to be the distinguished fiber of G. So this is saying that KGB elements 0 through 7 are in the distinguished fiber. And let's take the discrete series of discrete series gamma of G, and again, let's do rho of G. Oops. Sharp ds. There are 8 discrete series. Show the discrete series. So again, this is just like the previous example. The parameters themselves, they have the same lambdas, which is rho, and x is running from 0 through 7. Now, how do I make these look like the ones that I'm familiar with? Well, I have to look at these x's 0 through 7 and the corresponding compact roots. A more efficient way to do this is the following. For I in F, let's look at I and rho sub k of KGB element I. I got that right. So F is this fundamental fiber, so that's just the numbers 0 through 7. And I want to look at rho k of the corresponding KGB elements. Okay, so I look down this list and I see that 1, 1 isn't what I want, or nor is 1, 0, 1. Right here is what I want. Actually, there's 2 choices, but let's take 5. This is the row that I prefer, the rho k that I prefer. So that tells me I should say that XB to be KGB element number 5. And let's look at the simple roots of this corresponding K. There we go, 1, -1, 0, and 0, 1, -1. That's what I want. And so now let's do for P in the discrete series. Let's look at the Harish-Chandra parameter of P with respect to this XB. Now X while we're at it. I think there goes. Oh, yes. Do. There we go. That's better. All right. So let's take a look at this. I claim that these 8 lambdas are indeed the conjugates of rho modulo the action of WK. So these are another way to say that is these are the conjugates of rho which are K dominant. So K dominant means simply decreasing. So 3, 1, -2, 2, 1, -3, 3, 2, -1. All of these are decreasing. And there are 8 of them. And so indeed, these are the usual Harish-Chandra parameters of the 8 discrete series of SP6. Okay, so I'm looking if there's question. Adam's suggestion worked. Good. Okay. All right. So that's well, that's the way you get your brain around the discrete series. I recommend that you use. Well, let me remind you. We could say the Harishchandra, excuse me, the discrete series xb minus 1 minus 2 minus 3, and the software knows what you're talking about. It conjugates it back to it makes lambda dominant, which it always does, and in doing so it conjugated xb to x7. X is equal to 7. All right. Well, so maybe I'll conclude with looking a little bit at KGB and some other Cartan subgroups. So remember in this, well, actually, I'm not sure I actually did print KGB. So let's look at this. Whoops. Oh, G is SP6. Let's do G is SP4. Okay, so these are the 11 elements of KGB that I showed in that picture earlier, and the fundamental fiber is these 4, which are going to Cartan 0. These 4 are going to Cartan 0, and then these 5, 6, 7, and 8, I believe, are attached to Cartan number 2. And you can see the picture that I talked about. I don't want to bring it up again, but the picture of KGB, you see this last element is the element of the Weil group. And so this is saying that the fiber over this element of the Weil group has 2 elements, KGB elements 5 and 6, and then 7 and 8 are lying over this element. And by the way, this element down here at the end, this hat, means Cayley transform, which is to say you just multiply on the left. So this 1 hat E is really means the Weil group element S1, and this means S2. On the other hand, a cross means conjugation. So this is the Weil group element 1, 2, 1. That's because you multiply by 2 and then you conjugate by 1, and so on and so forth. So so I think it's worth looking a little bit, sort of just to tie all of this together, at the 4 different Cartans and the 4 different Weil groups. Okay, so let me show you what I mean. So let's set H is equal to Cartan class of G number 0. And let's print Cartan info of H. So this is the compact Cartan right here. And well, there's some other information that I don't care so much about at the moment. And what I want to look at is the real Weil group of G with respect to H. And well, this takes a little bit of explaining, which I'm not going to do. It says that the real Weil group is this thing. And well, this is a theorem about describing so this is the elements of the Weil group which are actually realizable in G of R. And if you just run through what this says, everything here is trivial except that there's a Weil group of type A1. So that says that the order of this Weil group is 2. And so the number of KGB orbits for the compact Cartan is what? Well, it's 8. Let me write it this way. It's 8 divided by 4. And then there's also, well, sorry, that's it, period. 8 divided by 2 is equal to 4. And that's the Weil group elements 0, 1, 2, and 3. And let's look at the next Cartan. Let's look at Cartan in this carton. So this is the carton. This is the complex carton. This is a copy of C cross. Let's print the real Wahl group of this carton. So let's see. It says this is trivial. There's an elementary abelian 2 group of rank 1. That is to say, a Z2. And this is trivial, and there's a Wahl group of type A1, which is also Z2. So the order of this Wahl group is 4. And so the number of for this carton is 8 divided by 4, which is 2. Okay, and let's look. Let's print KGB of G again, and let's set X is equal to KGB element. We're talking about carton number 1, so let's say, let's take this element 4. 4. And let's do this thing where we act on it by the Wahl group. Let's see if I have that here. It is. I'm doing this to X now. So this says that if you start with element 4, the order of the stabilizer is 4 elements. The Wahl so here are the 8 elements of the Wahl group, and according to this calculation, elements, the identity is 0, 1, 0, 1, and 1, 0, 1, 0 all stabilize element number 4. That is to say, the order of this Wahl group is 4, and it's those 4 elements. And then there's the other element in this orbit is 9, and its stabilizer has order 4 also. Okay, and finally, let's look at the last carton. Let's look at carton number 2. Well, not the last one, the last non-split one. And let's look at the real Wahl group for this guy. This has order 2. Trivial, trivial, trivial A1. And so the number of KGB elements coming from this carton is apparently 8 over 2 is equal to 4. And let's look again, let's look at KGB. And let's take X to be, let's see, the one coming from this carton, we could take number 2. Excuse me, it's carton number 2, so that is KGB element 5. And then if we look at this Wahl group thing, we see that the number 5, the order of the stabilizer is 2, because and explicitly the stabilizer is the identity and this element, which is the long element of the Wahl, the long simple reflection. So the up here, the order of the Wahl group is 2, and so the number of orbits is 4, 5, or KGB elements 5, 6, 7, and 8. Okay, and then, well, it's sort of silly, I already did this, but just for completeness, if you looked at the split carton, when you look at the real Wahl group, it says that the real this WR term is a Wahl group of type B2, and well, B2 is C2, so of course this is 8, and so the number of orbits for the split carton is 8 divided by 8, of course, which is 1. And I did this example already, but let's just do it one more time. If you let X be KGB element 10, and you look, you see that the entire Wahl group stabilizes it. All right. Well, I think that's a good place to stop. Let me see if there are any questions. Nope. And so that's kind of an overview of KGB and specifically how it applies to discrete series representations. And what I'll do next time is the intermediate representations. So if you take an intermediate Cartan, the parameter for it is giving you a discrete series of the Levy factor. So to some extent, it reduces to this discussion of discrete series. But of course, that takes a little explaining. So hang on one second. Let me just close this window. Okay, so as I was saying, next time I will try and move on to the notion of general parameters. And that means that looking at the cuspidal data of an arbitrary parameter, which will give you a Levy, earthquake again, which will give you the Levy factor M, and you need to try and applying what I just discussed to the discrete series of M. All righty, I'll pause for a second. Chamber. Okay, there's a question here, chamber. I wonder what that question means. Brian said, I'll post his question here. Chamber? Well, good question. I don't know what, send me an email and I will post these on the web and see you in a few weeks. Bye-bye.